Let us see topic 2.6.2 Estimation of Errors of Chapter 2. Errors during measurement is inevitable, means it is unavoidable. See, it is not possible to take any measurement without any error. Errors are inevitable. Why so? Let me give you an example. Suppose we are measuring a length of a pen by any meter scale and the measurement comes 12.2 centimeter. So now the question remains whether it is 12.21 or whether it is 12.25 or whether it is 12.29. That has not been measured in the meter scale. So the error remains. We don't know. We are just writing 12.2, but we don't know exactly whether it is exactly 12.20. We don't know. It can be 12.20, but it can be 12.29 also. When it comes to 12.29, then 12.29 is quite close to 12.30. So we don't know whether it is exactly 12.20 or not. So this measurement is having some error. Now if we measure it by vernier calipers, let us say, and we get a result like 12.25, then again the question remains whether it is 12.250 or it is 12.259. That is not measured in a vernier calipers. So here also an error remains. So measurement without error is not possible. Luck by chance, sometimes it may occur that the length is exactly 12.2000 and we have measured it 12.2. So in that case, the measured value is very exact to the true value. So it is necessary to accept these errors and it is necessary to estimate the errors. And that's why this topic is there, estimation of error. We must be knowing how much is the error. Rather, we must be knowing the maximum value of the error. So let us see further. It is necessary to estimate the maximum possible value of error during the measurement. See, maximum possible value, not the minimum. We need to know what is the maximum error possible. Error can be estimated by three terms. One is absolute error, second is relative error or say fractional error, and the third is percentage error. From the observations, we can find out these three terms, and by these three terms we can estimate, we can judge that how much is the error. More specifically, the percentage error gives you percentage value of error. That means it gives you that how much percent of error is there with the measurement. So let us see one by one. Absolute error. An absolute error is the magnitude of the difference between the individual measurement value and the true value of the measurement. See, absolute error is the difference between the individual measurement value and the true value of the measurement. Here we need to understand one thing, that is true value. See, practically true value is not possible. If I give you one pen and if I ask you what is the true value of its length, then obviously you will measure it and will give you. But as I said, the measured value is having some error already. So there is no true value possible practically. So what we'll do, we'll take the mean value as true value that we are going to see further. We will take the mean value, the arithmetic mean value of all the observations will be taken as true value. So in absolute error, what we need to do? We need to subtract the individual measured value and the true value of the measurement. Absolute error of some physical quantity, let us say A, can be denoted by delta A. If the physical quantity's name is A, then the error can be written as delta A. If it is, let us say, F, then it will be written as delta F and so on. When we don't know the true value of the physical quantity, we consider the arithmetic mean AM as the true value. As I said already, when you don't know the true value, obviously we have to take arithmetic mean of all the observations. Let us see this in detail. Let A1, A2, A3 up to AN be the measured values of the physical quantity A. The arithmetic mean of these values will be AM is equal to obviously A1 plus A2 plus A3 up to AN divided by N. We can also write this AM as sigma I is equal to 1 to N AI upon N. So this is the very well a method of taking mean. So if you have taken some observations of any physical quantity, let us say A, so the observations are like A1, A2, A3 and so on. So this is the mean of all these observations. Now the error in individual measurement are delta A1 is equal to A1 minus AM. See, this is the error in the individual measurement. Means, let us say for the first measurement, if we discuss, for the very first measurement, which came exactly A1. So, delta A1 is the error in this first measurement, because we have taken delta A1 as A1 minus AM. See, AM is basically the mean value of all the observation, but it is considered as the true value of the observation. So, this is the difference between the first measurement and the true value, we can say, and so this is the error in the first observation. The same way, delta A2 is equal to A2 minus AM is the error in the second observation, and likewise for the nth observation, error can be written as delta AN is equal to AN minus AM. The above calculated errors can be positive in certain cases and can be negative in certain cases. But absolute errors is always positive and is denoted by mode of delta A. It's very obvious that some of the value of A1, A2, A3 and so on will be larger than AM and some will be smaller than AM. That's why some of the delta will come positive and some of the delta will come negative. But the absolute error is always taken positive, and so it is denoted by mode of delta A. The mean of the absolute errors in all the measurements is known as mean absolute error, that is delta AM. This is the mean value of all the individual absolute errors. So how to take that mean? Obviously, delta A mean is mode of delta A1 plus mode of delta A2 up to plus mode of delta AN upon N. Note here that you have to take mode, because as I said that absolute error is to be taken always positive, and that's why these modes are kept. So if any of the value of delta A1, A2 or A3 anything is negative, then also it will become here positive, and that way we will get a average value or say mean value of the absolute error. You can also write this term as delta AM is equal to sigma I is equal to 1 to N mode of delta AI upon N. If we do a single measurement, the value we get may be of the range of AM plus or minus delta AM. Obviously, if we take any single observation, then the value what we get will be of the range of AM plus or minus delta AM. See, again, AM is the average or say the mean value of all the observations taken, and delta AM is the mean of the all the deltas, means all the errors. So it is very obvious that the measurement what we do will be AM plus or minus delta AM. That means we can write the measurement finally as this term, A is equal to AM plus or minus delta AM. See, this is a representation of the measurement of physical quantity A with its true value and with its absolute error. Here we are representing this physical quantity A with its true value and with its absolute error. And here you can see it is plus or minus, because as we have said already that we need the maximum error possible. So we are putting here plus or minus delta AM. It is something like that. Suppose the length L is 12.2 plus or minus zero point 0.1. If I write this way, then it is well justified, because here 12.2 is the mean value, or say it is the true value, and plus or minus 0.1 when I am writing, that means the minimum value possible is 12.1 and the maximum value possible is 12.3. So this is how we can represent any physical quantity with its true value and with its maximum absolute error. We can also write that it is AM minus delta AM is less than or equal to A and is less than or equal to AM plus delta AM. This implies that any measurement of the physical quantity A is likely to lie between AM minus delta AM and AM plus delta AM. As I said in the previous example, the length will lie between 12.1 to 12.3, because there we have written 12.2 plus or minus 0.1. So when you say 12.2 minus 0.1, it is 12.1, and when you say 12.2 plus 0.1, it is 12.3. So we can say now the value will not go below 12.1 and above 12.3. That's why we are saying that the physical quantity is likely to lie between AM minus delta AM and AM plus delta AM. So by this absolute error, we can now say that what is the minimum and maximum value possible of that physical quantity. Now let us see relative error or fractional error. The relative error or the fractional error is the ratio of mean absolute error delta AM to the mean value AM. Means the relative error, or say the fractional error, is a ratio of mean absolute error and mean value. That means we can write delta AM upon AM. This is known as the fractional error, or say the relative error. Now percentage error. When the relative error or the fractional error is expressed in percentage, it is called as percentage error, delta A. This is also delta, but it is small delta. So the percentage error delta A is now delta AM upon AM into 100%. This is the final thing what we always require in any of the measurement, that is the percentage error, because here we will get the error in terms of percentage. Let us say in any measurement we get the error in terms of percentage like 0.1%. So we can conclude that if the error is 0.1%, then it can be ignored. But suppose in any case we are getting error of, let us say, 13%, then it is not ignorable obviously. So in that case we have to take all the observations back. So this way, by absolute error, by fractional error or say relative error, and by percentage error, we can estimate how much is the error.